throughout this unit, up until yesterday at least, we knew that light is a wave. We have four properties of waves that are exhibited by EMR. They are refraction, polarization, diffraction, and interference. We're not suggesting now that that's not correct. EMR is a wave, but we introduced the idea yesterday that EMR is also a particle. Einstein in 1905 suggested that EMR is a particle called a photon or a quantum of energy. And the energy of a photon, or this particle of light, is equal to hf or hc over lambda. In other words, it's related to the frequency and it's related to the wavelength. We're combining here the wave nature and the particle nature of light, right? The energy of a particle is related to the wave nature of that particle. Remember, h had two values, 6.63 times 10 to the negative 34 joule seconds, or 4.14 times 10 to the negative 15 electron volt seconds. And usually we're just going to use whichever one ends up being convenient. We have those four pieces of evidence to support the wave nature of EMR, but where's the evidence that supports the particle nature of EMR, or Einstein's photon theory? Well, we briefly talked about this yesterday. We said that when light strikes a piece of metal, sometimes an electron is ejected. This was discovered in 1887 by Heinrich Hertz. When light, or EMR of any type, strikes a piece of metal, an electron would sometimes be ejected. Not always, but sometimes. What caused an electron to be ejected? Well, Hertz reasoned that it must be the energy of the photon, or the energy of the light, that causes the electron to be ejected. He is right. It is the energy of the light that's causing the electron to be ejected, but his explanation beyond that wasn't right. He suggested that if an electron was not being ejected, then it must be because there was insufficient photon or light energy. How do we get more energy? Well, let's have more light, brighter light, more intense light, light that shines upon the metal surface for a longer period of time. In other words, you want more energy to get an electron ejected, you need more light. But observations that were made by Hertz and others contradicted this. They found, when they observed the photoelectric effect, that it didn't matter how much light you had. If that type of light didn't cause the electrons to be ejected, then it never would, no matter how much you had. This is where Einstein comes in 1905. He says that energy, or the light, is a particle. And the energy of that particle is related to the frequency. In other words, E is equal to h times f. So Einstein said, in his photon theory, you want more energy for light, you need not more of it, you need a different type. You need EMR with a higher frequency in order to get higher energy. And guess what? The observations that were made for the photoelectric effect completely agreed with this. They found that when visible light didn't cause the electrons to be ejected, didn't matter how much of it we had, visible light would never cause the electrons to be ejected. But if we upped the frequency to ultraviolet, then the energy may be sufficient to cause the electrons to be ejected. This is proof of Einstein's photon theory. Remember, we've still got the wave nature of EMR, but we've now also got the particle nature of EMR, as proven by Einstein's correct explanation of the observations that were made of the photoelectric effect. Let's define a couple terms. Threshold frequency. The threshold frequency, given by the symbol F0, will be the minimum EMR frequency necessary to eject an electron. In other words, if your frequency of EMR, your frequency of light, is below a certain value called the threshold frequency, electrons will not be ejected because the energy, right, frequency related to energy, if the frequency is below a certain value called the threshold frequency, the energy will not be high enough to cause an electron to be ejected. Now, going along with that is something that we call the threshold wavelength. That's not the minimum wavelength, though. That's the maximum wavelength. Remember that wavelength and frequency are inversely related to each other. So if you have to be above a certain frequency, you have to be below a certain wavelength. Threshold frequency, the minimum EMR frequency, you got to be above that. Threshold wavelength, the maximum wavelength, you got to be below that. Another term called the work function. The work function is given by the symbol W. It is the minimum EMR energy necessary to eject an electron. Now, that corresponds to the energy used up in ejecting an electron. Of course, how much energy do you need to eject an electron? Well, however much you're going to use up in the process of ejecting the electron. We have an equation for this one. Remember from yesterday that the energy of a photon is hf or hc over lambda. Therefore, the minimum energy, which is W, is equal to h times the minimum frequency, which is threshold frequency, or h times c over the maximum wavelength, which is the threshold wavelength. So work function, minimum energy, is equal to Planck's constant times the minimum frequency, or Planck's constant times c, the speed of light, over the maximum wavelength. Now let's relate what we were talking about before to these two terms that we just learned about. Photons, particles of light, quantum of energy that are below the threshold frequency will cause nothing to happen. If the frequency is below the threshold frequency, nothing happens. Photons that are above the frequency of the threshold frequency, electrons will be ejected. In a 1-to-1 ratio. So in other words, if you have one photon that's above the threshold frequency, one electron will be ejected. If you have 37 photons above the threshold frequency, 37 electrons will be ejected. You have one below the threshold frequency, nothing happens. You have 37 below the threshold frequency, nothing happens. Now, assuming that the electrons are ejected because we're above the threshold frequency, if you jack up the frequency even higher than the threshold frequency, then we don't get more photons, we get more energetic photons. Remember, the equation that relates energy to frequency is E is equal to h times f. If you increase the frequency, then you're going to increase the energy of the photon. And if the photon has more energy, then that provides more energy to the electron that's ejected. So the electron can have more energy. You hit something with barely enough energy to cause it to be ejected, it's barely going to be ejected. You hit something with way more than enough energy to be ejected, then it's going to be ejected with a lot more energy. It's going to be faster moving as a result of that. So still below the threshold frequency, nothing happens. But if we're above, one photon causes one electron, 20 photons causes 20 electrons, 20 high energy photons cause 20 high energy electrons to be ejected. What about this? Well, if you're above the threshold frequency, more photons will cause more electrons, because it's a 1-to-1 ratio, right? One photon, one electron, 20 photons, 20 electrons. If we're more photons and really high frequency, then we'll cause more electrons that are more energetic to be ejected. Two more terms here now. We've got stopping potential. Symbol for this one is V stop. That's a capital V, by the way, not a lowercase. It's not speed. It is the potential difference voltage, measured in volts, right, required to stop, hence the term stopping potential, stop an already ejected electron. Now that's not going to make a lot of sense to you on the surface here. An electron's been ejected. The photoelectric effect has already taken place. Why would we want to stop it? Well, you'll see why tomorrow, why you might want to stop it. It involves doing experiments to determine the threshold frequency and some of the other properties of particular metals. Bottom line is we might. There might be a reason why we would want to stop the electron after it's been ejected. If we did, then we would see that that stopping potential is related to the initial kinetic energy of the electron. Right? The electron's been ejected. It has a kinetic energy that's equal to 1/2 mv squared. That kinetic energy gets converted as the electron gets stopped, gets converted to potential energy. So we would say that the kinetic energy of the ejected electron is equal to 1/2 mv squared, but it's also equal to qv stop. Q being the charge of the electron, v stop being the stopping potential required to stop that electron once it's already been ejected. Finally, one more. I'm just going to apply the law of conservation of energy to this whole deal. Of course, remember from physics 20, EI is equal to EF. The energy that we start with in this whole process is the photon energy, right? The photon with a certain energy equal to h times f. This is Einstein's equation. The energy that we start with is going to be equal to the, what has the energy at the end? It's the electron. The energy of the photon that we start with is equal to the energy of the electron that we end with, except that's not quite right, because we use up a little bit in the process. Remember what we call the energy that's used up in the process of ejecting an electron? It's the work function. So the amount that we start with is the amount that we end with. The photon energy that we start with is equal to the amount that we end with, the electron's energy, plus whatever we used up in the process of ejecting the electron. Now this is a pretty versatile equation that we see here, and it's not on your data sheet. Put a little star by that because it's not on your data sheet. It's pretty versatile because in the end we can replace HF with HC over lambda if we need to. Replace EK with 1/2 mv squared, or we can replace it with QV. And we can replace the work function with H times F0, threshold frequency, or HC over lambda max. All kinds of different combinations of equations that we can use within this one. One word of caution though. We said yesterday that we can almost always use joules or electron volts whenever we want. We still can, almost always. But there is one situation where you can't. If you use 1/2 mv squared or QV stop, you must use joules. Anything else that we've seen so far, you're allowed to use joules or electron volts. If you're using 1/2 mv squared or QV stop, though, you've got to use joules. You have no choice. Now, if you're confused by that, what did we say yesterday? Just always use joules. Sometimes it means an extra conversion or so, but it's not a big deal. If you know how to convert, always using joules works. If you're comfortable with when you can use electron volts, when you can use joules, then save yourself the work and use whichever one's most convenient. So what do we have here in terms of a summary? Well, qualitatively, let's take a look at this table. If the photon that we're shining upon the metal is below the threshold frequency, or if it's above the threshold wavelength, right? Because threshold frequency, you got to be above. Threshold wavelength, you got to be below. If we're below the threshold frequency and we increase the frequency of the EMR, but it's still below, nothing happens. No electrons are ejected. If we increase the wavelength, nothing happens. No electrons are ejected. If we increase the intensity, which is the number of photons, nothing happens. If we increase how long the light is exposed to the metal for, nothing happens. Nice simple way of remembering this. If we're below the threshold frequency, nothing happens ever. If, however, we're above the threshold frequency and we increase the EMR frequency, so we go from visible light to ultraviolet, increasing the frequency gives us a higher photon energy. And a higher photon energy gives us a higher kinetic energy of the ejected electron. Think about that. Einstein said E is equal to hf, bigger frequency, bigger energy. Bigger photon energy, well, that leaves more energy for the electron that's being ejected. Increase the wavelength. Well, increase the wavelength, that's decreasing the frequency. So that's going to give me a lower photon energy, which is going to give me a lower kinetic energy of the ejected electron. Now we're still assuming that we're above the threshold frequency or below the threshold wavelength. Increase the intensity, the number of photons when we're above the threshold frequency. Remember, it's a 1-to-1 ratio. Therefore, more photons causes more electrons to be ejected. And if you increase the time of exposure, you're doing the same thing. You're just doing it over a period of time. Still a 1-to-1 ratio. More photons causes more electrons. Remember the demonstration we did yesterday in class? Through the paper represented the photons. At the person represented the piece of metal. We threw the paper at the person, one single photon below the threshold frequency, nothing happened. 25 photons above the threshold frequency, below the threshold frequency, nothing happened. Increase the intensity, nothing happened. But when we increase the frequency of the photon, we upped the ante a little bit from the piece of paper to the calculator. Had we actually thrown it, we would have seen that there would have been an electron ejected. We're above the threshold frequency now, and the more of them that we shine on above the threshold frequency would cause more electrons to be ejected, more ouches to be heard. What about mathematically? A little summary mathematically. Remember, we know that E is equal to hf. That's not unique to the photoelectric effect, but it's valid. We have the work function, the minimum energy necessary to eject an electron, or the energy that's used up, equal to h times the threshold frequency, or hc over lambda max. We also have the kinetic energy of the already ejected electron is 1 f squared, or q times the stopping potential. And we also have hf, this is the conservation of energy one, is equal to the kinetic energy of the electron plus the work function, the energy that's used up. We star this one. Why? Because it doesn't appear on our data sheet. And because it's pretty useful. We end up using this one probably more than half the time. Here are two examples for you, and then I'll let you work here. Example number 1 says the work function of a particular metal is 4 eV. I'm going to circle this because I may want to convert that to joules. I'm not sure yet. 2 photons are incident upon the metal, one with a frequency of this, another with a frequency of that, or a wavelength, I should say, of that. Determine if each of these photons will cause emission. Here's what I want to do. I want to determine, I know the work function is 4.00 eV. If I find the energy of this photon, I'm going to use the EVs, 4.14, because I've got a work function EV. If I find the energy of that photon, to be 4.1 eV, and that's what I do find it if I do the math there, then I would say yes, it's above the work function. The minimum energy necessary to eject an electron is 4. I just found this one is 4.1. That's big enough to cause an electron to be ejected. What about the other one? We're going to say the energy of this one is hc over lambda. Once again, we're going to use the 4.14 value. Do that one, I end up getting 3.5 electron volts. Work function's 4. Electrons ejected here? No, we're below the work function, below the threshold frequency, the work function. Electrons will be ejected from the first photon. Electron won't be ejected from the second photon. One photon, remember, one electron. For this one, one photon, no electrons for this one because we're below the work function, below the threshold frequency. Last example that I want to do with you. Wavelength of the EMR incident on a photoelectric surface is 5 times 10 to the minus 7. What is the speed of the electron if the work function is 0.50 eV? What do we got here? We got the wavelength. This is not the threshold wavelength. This is just not the maximum wavelength, it's just the wavelength that we have. We want to find V. The work function is 0.50 eV. I'm going to circle that. Don't know that I'm going to have to convert that yet, but circle it just in case. Listen, if you're not sure which equation to use, try that last one. Because it's so versatile. We can do so many substitutions into that. Like, for instance, HF becomes HC over lambda. Like, for instance, EK becomes 1/2 mv squared. And we got everything we need. Solve for V here. Notice the 1/2 mv squared, though? Remember what we said back here? As soon as we introduce 1/2 mv squared, we must use joules. If you're not sure, like, if that confuses you at all, just always use joules. Let's do that conversion here. When we do the conversion, we find that this is 8.0 times 10 to the negative 20 joules. So we sub in 6.63 for Planck's constant. That's our joule seconds value. 3 times 10 to the 8 for the speed of light. Wavelength is 5 times 10 to the minus 7. The mass we use is the mass of an electron because that's what's ejected. And the work function is now in joules because we introduced 1/2 mv squared into the mix. 8.0 times 10 to the minus 20. We get this number on the left side. It works out to be 3.978 times 10 to the negative 19. Going to take the 8 times 10 to the negative 20 over by subtracting, multiply by 2, divide by 9.11, and then square root, and we end up getting 8.4 times 10 to the 5. That's a typical speed of a moving charge, 10 to the 5, 10 to the 6 meters per second. So this seems like it might be a realistic answer. All right. We're going to set you to work here now. On the remainder of worksheet number 20, you did questions 1 and 2 yesterday. I'm asking you to do questions 3 through 15 today. Just a reminder, when we're below the threshold frequency or above the threshold wavelength, nothing ever happens. When we're above, you've got to remember that different things happen. Increase the frequency, the energy of the electrons is higher. Increase the wavelength, the energy of the electrons is lower. Increase the number of photons, we get not more energetic electrons, but we get more electrons. And, of course, remember the equations as well. They're on your data sheet in one form or another, except for this one. But remember that this one ends up being the most commonly used one. All right, let's take a look at worksheet number 19, please.